Yeah, I've started the recording. So welcome to the week 7 of problem solving sessions for the discrete mathematics course. And yeah, so what we'll do today is that we'll look at some questions about graphs. Okay, so before that, I just wanted to clarify so that there is no confusion. So it was just for this time that the session did not happen on Friday, but on Saturday. But from next time onwards, we will have the sessions on Friday only. Just letting you know so that there is no confusion. Okay, so what we will do today is we will do some um, examples on graphs, and I think you already know what a graph is. You essentially have a set of nodes and edges, and if we'll define the terms and things that we need as and when we come to the problem. So okay, yeah. Hi, Manisha. So okay, I'll just define the terms that we need for this question. So we'll define what is a cyclic graph. You need what is a uniform graph and what is a complete graph. Right. So yeah. So as you know, a graph is essentially a set of vertices and edges. And what are the representations of a graph? So how do you represent a graph?
Ma'am, we represent a graph by nodes and sides.
Right. So one is what is called a graphical representation, where you can tell me what are the nodes, and you can tell me. So you can say 1, 2, 3, 4 are the edge, are the vertices, and you can tell me that draw an edge from 1 to 2, draw an edge from 3 to 4, and so on. So this is one representation. Do you know any other method of representing a graph? Matrix, right? Akansha says so. You have a matrix representation, and one is what is called an adjacency matrix, where what you do is you have the set of vertices on the rows, and you have the set of all vertices on the column, and then you say that if say vertex 1 here is connected to vertex 2, then you write a 1 here, and if vertex 1 is not connected to vertex 3, then you write 0 in the corresponding entry. So this is a Boolean matrix where you only have 0 1 values. That is right. So given a graphical representation, you can always define an adjacency matrix for it, and vice versa. Do you know uh, any other representation which is similar to adjacency matrix, but it's a different, um, slightly different from it? Okay, have you heard something called incidence matrix? So incidence matrix is that you have you have the set of vertices on this side, and you have edges on this side. So instead of the only difference is, instead of vertices here, you have edges here. And what you do is, if vertex 1, so you label the vertices and the edges. So this is e1, e2, e3, and so on. So on this side you will have e1, e2, e3. On this side you have 1, 2, 3, 4. And say vertex 1 here is incident on the edge e1 is incident on the vertices 1 and 2. So you write a 1 here and a 1 here, and zeros everywhere. Similarly, can you tell me the entries for this column? This is 2, by the way.
Ma'am, In the vertices column, we can write 1 at 2 and 3 plus and 0 at remaining places.
Exactly. So you can write 0 1 1 0, and for E3 you can have 0 0 1 1. So do you observe something? So if I give you a graph which does not have multiple edges or self loops, then what would this matrix look like?
Ma'am, it would look like a truth table, I think.
Okay, but is there anything anything special about this that is not there with, say, adjacency matrix or something? So one thing that you might have observed um, is that every edge is incident on only two vertices. So when I write an edge here, you can only have two ones. Okay, and the rest of them, no matter how many vertices you have, whether those are 50 or 100, the rest of them will always be 0. So if you sum up the column, you will always get 2. So this can be useful in certain cases. This property can come to use if you want to do certain computations. Is the observation fine with everyone though? Okay, good. So there is one more represent yeah. So there is one more representation that we will discuss, which you might have seen in the if you manage to look at the lectures. It is called degree sequence, and this is not a representation per se, but it's a method of describing a graph. So it's a way of describing a graph. This is called degree sequence, and whether you know this or not, for now don't worry, we will define this when we come to it. And it is slightly different from the three of the representations that we saw, but we will come to it when we'll cross that bridge when we come to it. So for now I just want to define some basic definitions of certain kinds of graphs. So um, yeah so right, so given a graph, you know uh, you know what a degree is, right? You have the degree of a vertex, which is defined as the number of edges incident on it. So for example, for the vertex 1 here you have degree of 3, and for the vertex 2 here you have degree as 2, and so on. So right, so now you say that a graph is uniform if every vertex have the same degree. So for example, if I have a graph like this, mm, okay, like this, then the degrees, what are the degrees of the vertices here? These are the vertices. Right, the degree of each of the vertex is 3. So this is a uniform graph. And in this case, it so happens that this graph is also complete. So what do we mean by complete graph? Each vertex has, so if your graph has n vertices in G, then degree of V is equal to n minus 1 for every vertex. So in this case, the number of vertices is 4 and the degree of each of the vertex is 3. So the graph is complete in the sense you cannot add more edges to it. It is already full. So all the edges that you could possibly draw without adding multiple edges are already there. So that is what we mean by a complete graph. And this is an infinite family. So for example, this is called K3, K4, which is a complete graph on 4 vertices. Can you tell me what does K5 look like? So I have 5 vertices.
Ma'am, it would look like a pentagon and a star in it.
Okay, right. So you draw all possible diagonals in the pentagon that you have. Yeah, so this will look like a star in the, yeah. So yeah, that is the idea. So this is an infinite family of graphs. So you can similarly have k6, k7 and so on. Right. So the only difference between uniform and complete is that in complete the degree is fixed, whereas in uniform the degree can be anything, but between 0 to n minus 1, but it has to be the same. So for example, this graph, I'll draw it here. So in this space, so this graph, is it uniform?
Yes,
Yes, this is uniform, but it is not complete. Uniform but not complete. Whereas this graph is uniform and complete. And uh, the third thing that will define is what is called a cyclic graph. So a cyclic graph is simple. You say C is a cycle of length n if you have n vertices, and say in this case I have 5 vertices. What you do is you draw a path from a path that passes through all the vertices. Then you look at the final vertex and join it to the first vertex. So if I pull this diagram, it will look like this pentagon. Okay, so this is a cycle over 5 vertices. This is what you call C5. So C4, for example, would look like this. So, what can you say about a cyclic graph? Is it uniform or is it complete, or can you say anything?
ma'am, I think cyclic graphs are uniform.
Right, exactly. Because the degree of every vertex is 2, so d of v is equal to 2 for all vertices in the graph. Therefore, it is uniform. But it is not complete. It need not be complete. So, yeah, so now that the definitions are clear, maybe try this example. So you're given this graph and you want to tell whether the graph is cyclic, regular, complete, or yeah. Okay, right. So Ojas and Akansha, yeah, both of you have correct answers. So this is in fact a cycle over 5 vertices. So you can pull this and write it like this. So you have B, C, D, A, E. So if you just rearrange the edges, then you essentially get this graph, and this is nothing but a C5. This is a cycle over 5 vertices, and like we said earlier, this is regular. So sorry, I think I've been using the wrong term all this time. So maybe I think I should correct. So this is called regular, and yeah, and I think yeah that okay. So yeah, like we said earlier, so cycles are regular and it's a cyclic graph, and it is not complete because you can still add edges like this which are not there. So it's not that you've added all possible edges, so it's not a complete graph. And okay, just as a follow-up question, how many edges would be there in a complete graph over n vertices? Right. So yeah, so that would be n choose 2, because you yeah, for every edge you have choice of two vertices, and yeah, that is all possible edges you can essentially add. And what about cyclic, uh, a cyclic graph on n vertices? How many edges would be there? Okay, is it 2n or is it n? Right. So yeah, good. So this is n, because I mean, yeah, you essentially draw an edge between adjacent vertices. So, for example, you have 5 vertices here and you have 5 edges here. So, the number of edges in Cn is, yeah, and mm, okay, maybe let's try this out. So, let's say you have a d-regular graph, as in the degree of each vertex is d. So, what is the total number of edges here? Okay, and there are n vertices. So, what would be the total number of edges? Right, so that is correct. So, this is your handshaking lemma, where you know that the total sum of degrees um, of vertices is twice the number of edges. This is simply because if you look at an edge, then um, it gets counted twice. It gets counted once in the degree of this vertex, and it gets counted once in the degree of the other vertex. So, by a simple combinatorial argument, you can show this, and just plugging the values here, you get dn is equal to 2 times the number of edges. Therefore, the number of edges here is dn over 2, which is what you have answered. Okay, good. So, the answer for this is B. And yeah, if there are no questions, I'll move on to the next one. So, okay, I think this is something you already answered, but maybe just calculate and let's see. So, you have a complete graph on 27 vertices, then what would be the number of edges? Okay, so Akansha says D. So, we know that if you look at a complete graph on n vertices, then the number of edges is n into n minus 1 over 2. In this case, n is 27, so you get 27 into 26 over 2, which is 27 into 13, and yeah, and that turns out to be 351. So D is your yeah, so D is your correct answer. I hope there are yeah, are there any questions about this? Okay, so just okay. Okay, so yeah, let me just define quickly what a tree is. So uh, a tree is an acyclic connected graph. So what do we mean by that? So a connected graph, so maybe I'll define each of them individually. So what is an acyclic graph? An acyclic graph is the one where you do not have cycles. And What is a connected graph? A connected graph is the one where if you give me any two vertices, I can give you a path between the two. So for example, if this is a graph that I have 1 2 3 4 5, and I tell you that from any vertex to any vertex, so for example between 1 and 4 you have two paths. I mean, that is not necessary, existence of one path is also sufficient. So yeah, so there is a path between these. In fact, if I remove this edge and I just simply give you a path like this 1 2 3 4 5, this is also connected, because if you want to go between say any two vertices here, you have a path that takes you from one to the other. So that is what a connected graph is. But something like this, for example, is not connected because you do not have uh, an edge or a path that will take you from this vertex to this vertex. So this is not a connected graph. And what a tree is essentially a connected graph which does not have cycles. So if you yeah, so what it would turn out as is you start at a vertex, then you have some children of, I mean, yeah, then there are some children nodes, then you cannot go back from this vertex to this vertex, or from this vertex. Essentially you can't go back from this layer to this layer, because if you do, you will end up getting a cycle. So the only possibility is you move forward. Okay, something like this. And again the same logic applies from any of the new nodes that you have created. You cannot have a path to any of the previous nodes, because if you do, then you would end up getting a cycle. So if I say draw something like this, then I get a cycle which is 1 2 3 4. So it's a cycle of 4, of length 4, and so on. So you can see this for yourself, and the same thing continues. So you can't go back, so you only keep moving forward. And the yeah, and the point where you stop is the um, so the nodes that would be there, these are called the leaves, and the other nodes are what are called the internal nodes. So yeah, so that is tree for you. Now the question um, is that you have a tree with 2048 vertices. What can you say about the number of edges in it? Okay, what about others? Ojas, Manisha? Right. So the answer is B, which is that um, you can show this thing in general. So if you have a tree with n vertices, then the number of edges in the tree must be n minus 1. And how do you show that? You can show this using induction, or um, okay, maybe just for an example. So let's say you have a tree over 3 vertices, then the number of edges that you have is 2. And yeah, and then you can inductively argue that, say you have some structure with k vertices, and there are k minus 1 edges at this point. This is your induction hypothesis. And what happens at the induction step is you add one more vertex, and since it's a connected graph, it has to have one edge with some vertex here, and you cannot have multiple edges because otherwise it would create a cycle. So the only way to keep it acyclic and connected together is that you add one edge. So then your total number of, so you have k plus 1 vertices, and the number of edges at this point becomes k minus 1 plus 1, which is k. And that is how you prove this by principle of mathematical induction. So I just gave you a very quick sketch of the proof because I think you're familiar with these arguments and inductions by now. So, but if there are any questions, then please let me know. So by that argument, since n is 2 here, by using this theorem, since n is 2048, the number of edges would be 2048 minus 1, which is 2047. So yeah, so I think all of you got it right. But if there are any questions about this proof or anything that we discussed, then please let me know. Okay, so if there are no questions, then I'll move on to the next one. So yeah, so you are given a graph which has 5 vertices, and these are the degrees that are given. So 1 1 2 3 3, these are the degrees of the 5 vertices, and the question that we are asking is what is the number of edges of this graph. Okay, so there are a couple of answers in the chat. So let's understand how. Let's try to solve this. So what we know is we mentioned earlier that okay, one thing you can do is you can definitely try to draw a graph with these degrees and then count the number of edges. That is also one way of doing it. But we can also use the um, tool that we just now learned, which is called Handshaking Lemma. And what does it say? It says that the sum of degrees of all the vertices is same as 2 times the number of edges in the graph. So now you know all the degrees, you know the degrees of all the vertices. Therefore, you essentially know the term on the LHS, and that would give you, if you divide it by 2, that would give you the quantity that you're looking for. So, what is the sum in this case? This is 1 plus 1 plus 2 plus 3 plus 3. This is equal to 2 times the number of edges. Therefore, the number of edges is 5, because this sum is 10. So yeah, so that is so yeah, so anybody, did you try to draw a graph which satisfies these degrees, I mean these constraints? I had constructed one at that point, at some point of time, but let me see if we can do it again. Okay, so this is one example where the degree of this vertex is 3 because there are 3 edges. Then this vertex is also 3 because there are 3 edges, like that. Oh, okay, sorry. This is okay, this is not.
Ma'am, I constructed a graph now that satisfies these degrees.
Yeah, can you tell me?
Yes, ma'am. First, you draw 5 points in shape of pentagon, and then join the 3 points in shape of triangles means 1, 2, 3. Join these three and join 3 to 4 and 1 to 5.
Okay.
Join 1 and 3.
Okay.
Yes.
So you have 3, 1, but then 4 also. Okay, right. Yeah. 1, 3 and 2. Yeah. So good. So this is one such graph which has degree sequence that matches with this. So do you think uh, given a degree sequence, um, okay, so first of all, if I give you a degree sequence, can you always come up with a graph?
No, ma'am, I don't think so.
Right. So we will look at some questions like that in after maybe a couple of questions. Um, Also, do you think if I give you a valid degree sequence, then is the graph that you can come up with, does it have to be unique? So in this case, I'm not sure if there is any other possibility for the graph, but in general, do you think it should always be unique? If not, then do you have a counter example?
Ma'am, I think it has to be unique.
Okay. Okay. Others, what do you think? Akansha, Manisha? Okay, so I think I think it need not be unique. So let's see. Okay, I have a counter example in mind. Let's see whether that is correct or not. So suppose I give you a degree sequence like this. So there are 6 vertices, and all of them have a degree of 2. So what all graphs can you come up with which have this um, degree sequence?
Uh, Ma'am, we can think of six dots and join them all.
Exactly. So you can think of it as a cycle, but you can also think of them as two cycles of length 3, because we never said that the graph should be connected, right? So in even in this example, the degree of each of the vertex is 2, but these are different graphs because if you look at the adjacencies, those are different. Is this fine? um, Okay, so the answer to this is no. Now the next question that I mean I just want to pose it. I have not thought about it whether what so now in this case, what happened is you have two different graphs for the same degree sequence, but if I ask you, is the connected graph unique? Then I'm not sure. I did not think about it also. I'm not sure if the answer for this is yes or no, but yeah, if you have any thoughts, you can let me know, or you can think about it offline. I'll also think about it offline. It just occurred to me right now, so I just wanted to pose it to you. Um, okay, Okay, Ojas thinks the answer is yes. Why do you think so?
Ma'am, because when we are given a degree sequence, we can think of two graphs, connected and not connected. And if we eliminate the situation in which the graph is not connected, then only one remaining is connected. So it has to be unique.
Mm, but why can it not be that there are two connected graphs, but they have um okay. Hmm. Okay, I think okay now I am also thinking that the answer to this is yes, but to prove this um, I mean to make such a claim, you will have to prove it formally. So it will have to go through like series of mathematical statements and conclusions. But I think my guess is that yes, it is. I think I agree with you. I think it's a connected. I mean, the answer for this may be yes, but yeah, proving this maybe may take some more work. Okay, uh, good. So, okay. Right. So, are there any questions about anything that we discussed so far? Okay. So, we'll move on to the next question. So, um, Alice and Bob are friends, and Alice is telling Bob that she has a graph with 32 vertices and 25 edges. But Bob is not sure. Alice is not showing the graph to Bob. She's just saying that she has a graph with these many vertices and these many edges. So Bob is not sure. So what do you think Bob can find out if Alice is telling the truth or whether she is lying? Yeah.
Ma'am, Alice is saying that she has a connected graph. So it can't be that she has 32 vertices and only 25 edges in a connected graph. So Alice is lying.
Exactly. Yeah. Good. So the key to this is the word connected. So if you have a graph that is connected, so or you can even generalize this. So you can say that if G is a connected graph with n vertices, then the number of edges must at least be n minus 1. So this is coming from the tree argument, because a tree is the minimal graph which is connected and acyclic. So the moment you add more edges, you will end up getting cycles. But in connected graph, we are not saying that we don't want cycles. Having cycles is fine for us, but we just want it to be connected. So that's why this at least thing comes up. So if you add one more constraint here, that you also want it to be acyclic, then this will become an equality. So like Ojas also said, so and the idea is very simple. So if you have, I mean, it's the same idea. If you can show this inductively, you can assume that okay, maybe for the base case you can say this is your graph which is connected, because the moment you remove this edge, these vertices will become disconnected. So for connecting two vertices, you need at least one edge. This would be your base case, and the induction step is exactly the same. So you can say that this is your graph on k vertices which is connected, and by hypothesis you know there are k minus 1 edges, and now you are adding one more vertex to the graph. So if you just add the vertex without adding any more edges, then it would not be connected, because this vertex has no way to reach to any of the vertices. So what you have to do is, in order to make it connected, you will have to add at least one edge. This is the same idea as the inductive argument for the tree. So therefore the number of edges would become at least k minus 1 plus 1, which is equal to k. So that would do the induction step for us. This is the induction hypothesis. So the idea is the same. Right. So using that, now you know that n is 32 and you have a connected graph. Therefore the number of edges must be 32, at least 32 minus 1, which is 31, which is clearly more than 25. So Bob cleverly uses this idea that in a connected graph, if you have n vertices, then the number of edges is at least something. So using that, Bob figures out that Alice is lying. So yeah, uh, yeah. So is this fine with everyone? Okay. So I'll move on to the next question. Um, so I'll just define what connected components are, because you need this for solving this question. So suppose I draw a graph like this. Okay, then this is a graph G. Then what you do is, you start at this vertex and tell me, I'll color them with, okay, for that to happen I need to number them. So this is 1 2 3 4 5 6 7 8 9 10. So these are the labels of the vertices, and what I'll do is, I'll start my tour from, let's say I'm standing at vertex 1, and you tell me what all vertices can I reach from there. So I'll start coloring them with red. Yeah, you can tell.
Then we can reach to vertex 2,
2.
then 4 if the edge is given,
Right.
and 3 also.
Right. And can you reach to any of the vertex here?
Uh, yes, ma'am.
How do you reach from 1 to say 5, or which vertex can you reach to from 1?
Ma'am, are these two graph separate, or this graph 1 is a part of second graph?
Yeah, so all together this is one graph. So a graph need not have all possible edges. I mean, right, for example, if I give you 4 vertices like this where there are no edges, that is still one graph. Right? So just like that, this is one graph that is given to you. And
Then from 1 I can reach every point 5, 10, 9, 6,
how do
7,
you
8.
what is the path that you follow to reach to 5, for example?
I will join 1 to 5.
But 2 to 5 is not an edge, right? The edges are only the blue colored.
Oh, oh, now I get it. Then there are no other points that can be. Uh,
Exactly. Exactly. That is, yeah. And now let's say I start at 9, for example. Then what all points, maybe I'll take some other color. So, right. So maybe I say start at 9. Then what all points can I reach?
10, 5, 6, 7, and 8 also.
Exactly. So what happens is, if you keep on doing this process, you pick a vertex at random and color them with red, all the vertices that are reachable with red. Then when you can't go forward, you pick another vertex at random which is not yet colored, and go to all possible vertices you can reach and continue the process. So in this case we did this step 2 times and we are done. We have covered all this graph. So what you do is, now you form a partition of the graph based on the color that they have. So for me the red ones are one part and the blue ones are the green ones are the other part. So this is what is called a connect these are what are called the connected components of a graph. That is, um, within themselves they are entirely connected, and but if you look across them then none of them are reachable. So does this remind you of any relation that you must have seen? So just as a follow-up question, so what is a relation? You define R as a relation um, from V cross P, and say U V are related if there is a path between U and V. So is the relation clear? So for example, in this case 1 and 2 are related because there is a path, but 1 and 5 are not related because there is no path. So what kind of properties can you I mean say about this relation? Is it symmetric, reflexive, transitive?
Ma'am, I think it is transitive.
Okay, right, it is transitive because if you have a path from U to V and you have another path from V to W, then you have a path from U to W. That is correct. um or I mean, it need not be path, it's just a trail or tour or anything. So what about symmetry? Notice that we're talking about, yeah, we're talking about undirected graph here. That's why it is symmetric. So if you have a path from U to W, then you also have a path from W to. And what about reflexive? So you can always reach a vertex. I mean, if you start at 1, you can always reach at 1 by not taking any edge. So it is reflexive. So what do you say if this three properties hold in a relation? What is the name for this kind of a relation? Right. So Akansha says this is equivalence relation. And if you remember, we had discussed about equivalence classes where you do a similar thing. You pick up you pick up an object and you look at all the elements that are related to it, and then you form such similar clusters. So I mean, if you remember, I'm just trying to connect. If you do not remember, you can go back and revise. So let's say this is the set of all the elements. What you do is, you say that if the relation is an equivalence relation, it's going to partition your set into classes which follow two properties. One is that, okay, yeah, if anybody remembers, so would you like?
Ma'am, one of the properties, they are all disjoint sets.
Correct. Yeah, that is yeah, that follows from the two properties that we will okay. But yeah, good. So the properties that we said is that if you look at any two elements within the class, they will always be related. If you look at two elements across the class, any two elements that are across the class, they would never be related. So if U V are in the same class C, then it has to be that U V are related. And if U V are in different clusters or classes, then it has to be that U is not related. UV is not related, are not related. So that by these two properties, you can conclude that like Ojas was saying, that these are disjoint clusters and they are also exhaustive. So that is essentially what is happening here. So if you look at any two vertices in this cluster, they are always going to be connected, and if you look at any two vertices across the clusters, then they are never going to be connected. So there is an underlying relation in action. I just wanted to um, bring that out, but that is not important for the question as such. But I hope that helps you connect two things. So right, so that is what connected components are for us. So given a graph, it's you can always partition them into components that are connected by themselves, but across any two components they are not connected. So what is the question? The question is that you are given k connected components, I mean a graph G which has k connected components, and the number of vertices in each of them are n1, n2, and so on up to nk. The question is, what is the maximum number of edges that this graph could have? Okay, Akansha says A. Okay, Ojas, Manisha, what do you think? Sorry. Okay, so let's try to solve this step by step. So so let's try to draw this graph. So you have this graph G where you have k components. So this is one component which has n1 vertices, 1 2 up to n1. You have the other component where you have n2 vertices, and then you have all the way up to nk vertices. So let's ask a question. What is the total maximum number of edges you can have in this component C1? This is a connected component. Otis, what do you think? So the maximum number of edges in C1 which has n1 vertices and it is connected. N1 choose 2. Exactly. And similarly, in the component 2, the maximum number of edges you can have is n2 choose 2. And in the final component, you can have nk choose 2. Now the question is, can you have an edge apart from this? So what would this look like? This will look like a complete graph on n1 vertices, complete graph on n2 vertices, and so on, right? Now the question is, can you have more edges? Can you, for example, have an edge that goes from the first vertex of C1 to first vertex of C2? Good. So you can't have such an edge because it will violate the property of the definition of connectedness. What we said is these are two different connected components, and hence you cannot have any edge across them. So the only edges that can have that you can have is inside the components, and we are just maximizing them. So the total number of edges that now you can have is OJs. So can you complete the next step? Okay, so the maximum number of edges that you can have is the maximum edges here plus here plus here and so on. So that is n, sorry, this is equal to n1 choose 2 plus n2 choose 2 and so on up to nk choose 2, which as Akansha said, this is same as ni choose 2 I in 1 to k. So is this making sense, or are there any questions about what we did?
Ma'am,
Mm-hmm.
what we just find, is this connected to the number of means cardinality of equivalence?
Cardinality of equivalence set. mm, yeah, you can say that, but there is no notion of complete completeness for a relation. So here we had a nice notion of what is a complete graph, where you can have maximum possible edges, but for relation we typically don't talk about it that way. So I mean, you can define that term, and then what you are saying is correct. You can say a similar thing in the relations world, but typically we don't naturally talk about um, relations as number of relations or the cardinality of relations. But yeah, okay, good. So that brings us to the next question. So you already know what a degree sequence is. It's just the degrees of the vertices of the graph that is written in a sequence. So the question um, is um, is that you are given this degree sequences A, B, C, D, and you want to find out whether you can form a valid graph out of it or you cannot. So take your time. Um, I'll just take a quick break and I'll be back. So in the meantime, you can try this out. Okay, so so Akansha and Ojas, both of you say, um, yeah, D. So what is your strategy? Like, how do you conclude whether it is a degree sequenceable or not?
Ma'am, in option D, I just applied Havel-Hakkini's theorem,
Mm-hmm.
and it could not satisfy. Means in last step, it could not give all zeros or stars. That's why it is the right answer for this question.
Right. Good. Uh, right. So, okay. So what you did is you applied Havel-Hakkini theorem, which says that okay, maybe we will do this with example. I'll not define this in general, but let's look at a degree sequence which is 6 5 7 6 5 4 4 3 2 1. So these are 7 vertices, and what the theorem says is, so this is say my sequence 1, and what you've done is you have arranged it in non increasing order. So what the theorem says is, you look at this first vertex, which is, I'll call this A, B, C, D, E, F, G, H. And what you do is, from this vertex A, you add um, you add 7 edges to the vertices in order. So that would be B, C, D, E, F. Mm, okay, wait. Uh, Sorry, these are 8 vertices, right? Okay, that makes sense. Right. So yeah, you add 7 edges like that to all the edges in order. So now what? Now let's say I remove this vertex. Let's say I remove this vertex A from the graph and the edges that are incident to it. Then what does the degree sequence of this becomes? This becomes 5 4 3 3 2 1 0. And now what your Havel-Hakkini theorem says is that if you can draw a graph for this, or this is, if you can draw a graph for a sequence, then it's called a graphic sequence. So if this is a graphic sequence, then this is a yeah, Ojas, you have a question?
Ma'am, it's not a question, but
Mm-hmm.
in this question, in option D, there are 8 vertices, and the degree of first vertex is 8, and that cannot happen. So by
Exactly.
that method, we can get answer to this question.
Exactly. So that is a very nice observation. So what Ojas is saying is, you have only 8 vertices in this graph, and uh, therefore the maximum degree that any vertex can have is 7. And here clearly the degree of one vertex is 8, which cannot happen. So you don't even yeah, you don't even go to the Havel-Hakkini theorem. You can there, then and there you can conclude uh, without using the theorem. So that is a good observation. And yeah, maybe uh, I'll talk about some other attempts after we just go through how to apply the Havel-Hakkini theorem. So yeah, then what you do is you pick the next vertex, which has yeah, uh, then you add 5 edges from this vertex B to the next 5 vertices. So this is 1 2 3 4 5, and then you would end up decreasing the degree of each of them by 1. So you get 4 3 2 2 1 0 0. And now you repeat the same process. So what would be the next sequence?
Ma'am, it would be star star 211000.
Mm, okay, just a second. Okay, did I make a mistake here? Sorry. You're adding five vertices, so this should have been star here itself, right? So this is already star. This is also star. Yeah. Sorry, that was yeah. Sorry. This shouldn't have been four. This should have been star. And yeah. So what would be the next step?
It would be star 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 11 and 000.
Right. And the next one.
Four stars and four zeros.
Um, right. So yeah. So now what this tells you is if you reach a sequence which is just composed of stars and zeros, then it is a valid. This is a valid Havel-Hakkini sequence, and therefore inductively, I mean, yeah, the same argument holds. So since this is valid, this is also valid, and therefore this is valid, and so on. So can you construct a graph now? I mean, given this sequence, can you construct a graph which satisfies this sequence? So what would that look like? Maybe I'll draw. Um, okay, I don't know if it's difficult to draw, but let's try it out. So let's say you have A, B, C, D, E, F, G, H. Yeah, or maybe sorry, I'll rearrange this. So let's say you have A, B, C, D, E, F, G, H. Okay, so what would this graph look like?
Ma'am, first we have to connect all the points to A.
Okay,
Then the remaining points to B.
okay, because degree of B is 6. Yeah, so you have 1, 2, 3, 4, 5, 6.
Uh, then we can join any of the 3 points to C.
Any of the 3 points, or you do it in order, because that is how we are doing this process, right? You are deleting one, I mean decreasing the degree of each vertex by one in this order. So what you do is you connect C2, okay, C2, um, three vertices, okay, then
Then
D1,
D, yes,
D2A, and this already gives you, right? Yeah.
yes.
So this already gives you a graph which satisfies the degree sequence that is given. So this is 7, 6, 5, 4, and 2. Sorry, this is 4. Um, this is 3, 2, 2. So this matches with the sequence that is given to you. So the point that we are trying to make here is that if you have so this Havel-Hakkini theorem not only tells you whether the graph is uh, I mean it's a valid sequence for a graph or not, it also gives you a constructive method of actually finding the graph. So um, yeah, so one question that arises at this point is, why does it matter, when we were trying to draw, or just said that um, you can say add C has currently okay, I'll put it this way. So you have A and you have added this 7 black edges at this point, then you go to B and you draw 6 blue edges at this point, and you move to C, and we know that the degree of C is 5 and 2 edges are already incident on C, so you have to add 3 edges. Now the question is, can you draw them arbitrarily or do you follow the sequence? So how is the sequence important is the question. So um, yeah, so what do you think? Can you do this arbitrarily or do you think you need to go in the sequence? So would this have worked, for example, if I would have just arbitrarily taken H, G and F?
No, ma'am, I don't think so.
Exactly. So yeah. So if you say, if you would have drawn edges like HGF, you have already violated this um, constraint. So it's important for you to follow the order and yeah. So again, the next question that you can ask about this is if you look at a given sequence, does Havel-Hakkini give you, so Havel-Hakkini tells you one way of drawing the graph, but are there other ways of drawing the graph, or is it a unique sequence? So this is somewhat similar to the question that we asked earlier. Can you have um, do you have a unique connected graph for the given sequence? So that is also something that is similar to this question, and you can think about it offline. And just for the sake of demonstration, yeah.
Ma'am,
Mm-hmm.
uh, just if we have in S4 like if we have 4 in place of 1, then
Mm-hmm.
what should we do?
If you have
So
4 in place of 1 here, here.
yes, in yes 4, yes 4.
Um, no, sorry. Are you saying the degree of H is 4 or?
Uh, no, ma'am. If we had a different sequence than this and we come up to an conclusion in step 4 that here it is 3 star, 2 ones and 3 zeros. If we had 3 stars and 4 and 4 zeros, then what should we do?
You are saying you have 3 stars,
1 4
1 4
and 4 zeros.
and 4 zeros. So yeah, so I'll come to this. I'll This is a good question. So what do you conclude from here? So to demonstrate, so to get there, maybe we'll try out this example so that for others who are watching the video, I mean, later on it will be clear. So that will answer your question. So I'll just take this sequence quickly. So you have 877 64211. Okay, this is your first sequence, and I think you will, in the first step itself, you'll get to the situation you are mentioning. So what is the first step?
Make uh, sorry, place star at the place of 8 and remove 1 from each of the value or degree.
Right, and then you don't have a place to decrease one from. I mean, so you can only get to one from here, and yeah, there is no way to, um, yeah, add one more edge. So okay, so I think this does not lead to the the state that you were telling, but okay. So I'll get back to this question. So now what is the next step in the Havel-Hakkini theorem? The next step, natural step, is you look at the next vertex which has maximum degree and you decrease its degree to 0. So you come to star star star, um, yeah, then this becomes a star. So this would become -1 -1 -1 -1. But now what happens is you cannot have a vertex in your graph which has a negative degree. So what this tells you is this is not a valid, or this is not a sequenceable graph. Sorry, this is not a graphic sequence. And therefore by your Havel-Hakkini theorem, if this is not a graphic sequence, then therefore this is not a graphic sequence, and hence you can go all the way up to where you started with, and this induces the same result, and you can conclude that it's not a graphic sequence. So what it tells you is, only if you reach ultimately at a point where everything is just stars and zeros, then it's a valid sequence. But if you reach to a stage where you do not, we have something else other than, basically you have negatives, then it's not a graphic sequence, and that is where you stop and conclude that it's not a valid graph. So yeah, so that was a, yeah, thanks for asking the question. So for the rest of them, I think I think these are, I mean, you can try this out yourself and check if it's sequenceable or graphic sequence or not. um, yeah, and about the proof of this theorem. So um, yeah, that, I think that was not covered in the course, but you can try this out on your own. um, okay, maybe I'll just ask you out of curiosity, what do you think, like how would you approach about proving a theorem like this?
Ma'am,
Mm-hmm.
I think we can apply like what induction analysis here.
Hmm.
Like there are n vertices.
Hmm.
Then the other sorry, if there are uh, like one to k degree on n vertices, then the other vertices have some n minus 1 to n minus k degrees.
Hmm.
That way we can prove this theorem.
Hmm. Right. Good. Akansha, do you also have something to say? You can maybe let me know in the chat, or you can unmute. Mm, okay. So yeah, you, if you are typing, you can keep typing. I'll just repeat what she said. Um, okay. So this is just what I am thinking at this point. Okay, I have not looked at. I mean, I have not. Um, I mean, I myself have not looked at the proof, but yeah, but I think the basic idea would be what, close to what you are saying. So the idea would be that if you are at a step, at the ith step of your applying this um, theorem, then this is graphic. This is a graphic sequence if and only if si plus 1 is a graphic sequence. And uh, so first thing that I want to convince you is that um, so like you said, this is an inductive approach. So you start at the first step, you say this is a graphic sequence, and hence this is a graphic sequence, and so on. So therefore, if you start with s1, you go to s2, and at the end this is your last stage. Therefore, let's say you conclude that sl is, what you ended up getting is just a string of stars and zeros. Maybe this is of length n, let's say, where n is the number of vertices. And if this happens, then what do you know about SL?
Then SL is a valid graph.
Right, this is a valid graphic sequence. So which direction of the which direction of this, if and only if, are we using if SL is a valid graphic sequence? Are we using the forward direction or the backward direction?
Uh, I think we are using a forward direction. Like if SL is not valid, then how can SL plus 1 be valid?
Okay, so just to be clear, the forward direction is that if SI is graphic, then SI plus 1 is graphic, and the backward direction is if SI plus 1 is graphic, then SI is graphic. So which one are you talking about?
Forward direction.
Mm, okay, that is so. Okay, so what is the conclusion from this?
No, ma'am. It is a backward direction. Backward.
Exactly. Good. So this is the backward direction. So what you're doing is now SL is a valid sequence. Therefore, you're saying SL minus 1 is valid. Therefore, SL minus 2 is valid. And therefore, ultimately, the sequence that you started with is valid. So what you're using is the backward direction in this proof. So why do you even need the forward direction then? Is it not enough to just do the backward direction?
Ma'am, because in the theorem, we prove and come to a conclusion of stars and zeros. So if that final conclusion is completely stars and zeros, then only the our first sequence is valid. Therefore, we use backward direction.
Exactly. Exactly. That is the point. So, in this case, it so happened that you ended up in a case where the final sequence was valid. But let's say, for example, you went from S1, S2 all the way up to SL. But in this case, you ended up with some negatives in uh, the final sequence. Then you know that this is not a valid graphic sequence, and therefore you want to say that if this is not valid, then SL minus 1 is not valid, and this inductively goes all the way here, and finally you say that the sequence that was given to you is not valid. So what we said is if Si plus 1 is not valid, then Si is not valid, and by the equivalences that we saw, this is basically contraposition of the statement that Si is valid, then Si plus 1 is valid, and this is where you use the forward direction. So therefore you need if and only if. Using backward direction, you can only conclude that the sequence is graphic, is valid, and using the forward direction you can conclude that the sequence is not graphic. Therefore both the directions are necessary. So if you want to prove the Havel-Hakkini theorem, you just want to prove this claim and the base case. So base case would be just this. That is simple. So how do you go about saying that if Si is a graphic sequence, then Si plus 1 is a graphic sequence?
Ma'am, I didn't understand the question. Can you repeat it?
Right. So I want to prove the forward direction of this claim. That is, I want to say that Si is a sequence which is graphic. Then I want to show that Si plus 1, which is the sequence obtained after one step of Havel-Hakkini, is a valid graphic sequence. So how would you prove this statement?
Can we prove it by contradiction?
Okay.
We assume that Si plus 1 is a valid graphic sequence and doing the steps according to Si and Si plus 1, we end up at the conclusion that contradicts our assumption.
Okay, okay, that might also, yeah, think that might also work out. But if you want to do a direct proof, it would be um, it would simply be that so you want to show that Si is valid, then Si plus 1 is valid. So what that essentially says is that you assume that there is a graph wherein, say, without loss of generality, let's say u is, so you have a graph like this right now, and then you have some digits here, some some numbers, and um, yeah, and there are some edges like this. So uh, yeah, so essentially what you're saying is that if this graph exists, then I can safely delete this vertex u, and I can delete the edges that are incident on it, and the graph that is remaining after that, which is this part, which is, it's called edge, is valid. So that is exactly what we are saying, right? So assume you have a graph which is given by this sequence, that follows from the assumption, and you're deleting a vertex. So that is exactly what is happening, right? You're just deleting a vertex and all the edges that are incident on it, and Si plus 1 is just the sequence of the remaining graph that you have. So since deletion is an operation that gives you this edge, then uh, yeah, then therefore this sequence is going to be valid. So does this make sense? Okay, and similarly, if you want to go the backward direction, it would be that you have a valid subgraph edge, and now you're going to add a vertex u. I'll maybe do it in different color. Now you're going to add a vertex u to the higher degree vertices in edge. Therefore, that would give you the corresponding degree sequence for Si. So since h is valid and you're adding a vertex u such that you have edges on the corresponding highest degree vertices, then therefore you get a valid sequence for Si. So it's just about adding a vertex and deleting a vertex. So at the moment, I think this is a sufficient argument to prove the theorem. But again, I'm not sure, I haven't looked at the proof, but I'm not sure if there are any more details that you need to any more working out that is needed. But on the surface it looks like this would be a sufficient argument, but it is worth taking a look at it. I'll also try to take a look at it, and you can also do the same. And yeah, the only other comment that I had was, let's say you do not, I ask you the same question. Okay, right. So was the argument fine? Whatever we were just trying to understand, if you want to prove a statement like this, then how would you go about it? So are there any questions about any of the directions? Okay, Akansha. Okay, so the only other thing that I wanted to, I'll just quickly try to state it. Suppose I ask you the same question, but you do not know Havel-Hakkini theorem, or let's say I don't allow you to apply this Havel-Hakkini theorem, then like you said, in this case, this one was an easy, like you can spot it easily that this is not a valid graph, because you can't have vertex with degree 8 in a 8 vertex graph. So but that may not always be possible, right? There may be some other violations that happen. So if I don't let you use this, and how would you go about trying to mm,
So, ma'am, I will use that brute force method, and so I will simply draw the graph with the given degrees.
right? So you can definitely, you can try to use the brute force and try to look at all possible graphs, and check whether you can achieve this sequence or not. But if the number of vertices is very large, or if the degree sequence is very large, then this can be a bit difficult to do, or it may be time consuming, whereas this theorem, for example, gives you a one shot, like a quick answer to this. So um, yeah, so I was just this is just something that I was thinking about. I haven't yeah, I mean, I'll just tell you the idea, and yeah, I'm not sure if it is always going to work out. I didn't try to prove it, but I'm just trying to tell you a possible approach using the things that you know. So what you know is a handshake is something called handshaking lemma, right? So um, yeah, so essentially, if you um, sum up the degrees of the vertices, then you know that this is equal to twice the number of edges. So what you can do is you can sum up the degrees of these vertices and look at the number of edges. Now the thing is, the number of edges here um, has a certain bound, right? Um, you cannot have more than n into n minus 1 over 2 vertices at edges at any point of time. Is this okay? Right. So the idea is that in this case, say let's say you sum up these degrees. So what does that turn out to be? So this is okay. You can help me out here. 10 plus 10 plus 10 plus
Ma'am,
12,
32.
32, right? So this is 32, and what we're saying is 32 is equal to 2 times the number of edges. Therefore the number of edges here is 16, and the number of vertices that you have is 8. So the total number of edges that you are allowed to have is 8 into 7 by 2, which is 28. So um, so this is valid, right? So far this is valid, right? So yeah, so what you
Ma'am,
mm-hmm.
and in the course, I also get to say that if a given degree sequence has odd number of odd degrees, then it can't be uh, plotted graphically.
Exactly. That is also another quick check that you can do. You can just you can be clever and see, just look at the number of odd degrees that are there in the sequence. If there are odd number of vertices that have odd degree, then you can just say that um, I mean, this is not a valid sequence. And yeah, again, you that follows from your handshaking lemma. So okay, so I'll just try to explain the idea, but even if it does not make sense, that is fine. I just wanted to give you something to think about. So, okay, so at this point, this is your first check. The first check is that look at the number of edges, look at the number of vertices, and yeah, if it is within this bound, then you are good. The next thing that you do is you delete a vertex which is of minimum degree. So in this case that is 1. So the sequence that you would end up getting is 7 6 5 4 4 3 1. It does not matter what the sequence is, because in the entire handshaking lemma you are just looking at the sum of the degrees. So now you can think of this as a graph with 7 vertices. Uh, right, you had 8 vertices initially. You can think of this as a graph with 7 vertices, and these are the degrees that you have. So now what you do is you do the same thing again. That is, you look at the sum of the degrees and equate it with the number of edges and count the number of edges. And so maybe let's do this once. Okay, so yeah, so the sum, what is the sum in this case? It was, I think that should be 30, right? So 30 is equal to 2 times the number of edges, so the number of edges is 15. And what is the total number of edges that I'm allowed right now? The number of edges allowed is 7 into 6 by 2, which is 21. So again 15 is less than equal to 21, so I'm good again. And then you keep on continuing this process. So you delete one vertex which is of minimum degree, and then keep on applying the handshaking lemma. Now my claim is that at the end, when you have exhaustively deleted all the vertices and at every point you have satisfied the handshaking lemma, then then if you have satisfied at every point, then your sequence is valid. And if you have at some point exceeded this number, that this allocated quota that you have from the handshaking lemma, then the sequence is not valid. So I have not I did not try to prove it or disprove it as such, but I just wanted to give you um, I just wanted to give you something to think about. So the point is that whenever you come across a question like this where trying brute force is hard and you need some kind of theorem, some kind of leverage to solve it, you can try to, before even you look at what is known, you can try to think about the small properties or lemmas or um, formulas that you know, and try to see if you can repeatedly apply them or apply them in some combination to um, to solve this. Because if you look at this theorem as such, um, it's very simple to see, it's very intuitive to see, and it's also easy to apply. So so I just want you to cultivate this thought process where you yourself try to come up with theorems like this, because that is how these things are these things have come up anyway. Somebody must have tried to use what you know, or yeah and like scratch your head and come up with theorems like this. So I just want you to keep an open mind and try out things on your own. So okay, so you can think about this if you like. I just wanted to mention this. Is the approach fine? Okay, good. So so you can quickly try this out. So what is a spanning subgraph? A spanning subgraph is the one where um, essentially you have covered all the vertices in the yeah okay, maybe since we have only 15 minutes, I'll take this question next time, but so maybe you can do the easier ones right now. So what is a cut vertex? Do you remember? Okay, so a cut vertex is something that um, okay, maybe I'll just take this same or maybe okay, let me take example of a cycle. Okay, maybe something like this. So this is my example. What I'm saying is, let's say I'm deleting this vertex. Let me call this vertex 1. Let's say I'm deleting this vertex. What would the graph look like? You would have something like this, right? So right, so what happens is you have disconnected your graph into two components. This is one component where there is only one vertex. This is the other component where there are four vertices. So if you delete a vertex and the resultant graph breaks into at least two components, then you say it is a cut vertex. So for example, if I delete this vertex, do you think the graph would break into more than one connected component?
No, ma'am.
Right, good. So this is not a cut vertex. So the question is essentially asking you, so cut vertex is the one where delete the vertex and the graph degenerates into more than one connected component. So so you look at this graph and um, try to find out what is a cut vertex, or
Ma'am, I think it should be option C.
option 3. Okay, so what are the cut vertices according to you? So G is a cut vertex.
Yes, G is
E
E. B and
B
C.
and C. Yeah. So the answer is C. Right. And right. So, okay, look at the same graph, and let's say I delete these vertices that you just told me. Say I delete G, I delete E, B, and C. If I delete all four of them, how many connected components do I have in the graph now?
There won't be any connected components in this graph.
Mm, so, if I give you a graph like this, where there are no edges, so how many connected components are there in this graph?
No connected component. Sorry, four connected components
Right.
because vertices join themselves too.
Right. So these are four connected components, and that is exactly what you have. You have A, D, F, and A. So you have four. So an isolated vertex is a connected component by itself because it is connected to itself. So you get four uh, connected components. Right. So um, yeah. So right. So I mean, I'll just ask some questions which you need not answer, or I mean, I'll just ask some natural questions that one can ask at this point. So in general, let's say you have a graph G over n vertices, sorry, a graph G with n vertices, and let's say there are k cut vertices. So what can you say about the number of components if you delete all the k vertices? So I'm just posing natural questions at this point. The answer to this may or may not be simple. I don't know. I'm just asking whatever comes naturally. So what is the number of connected components? So you can think about this. Also, if you have any questions that come to you in this I mean throughout the tutorial, if you have any questions that come up like this, then you then feel free to ask, or write, maybe use the forum or in the tutorial, because these questions lead to new results, because essentially a result comes up when, or a new theorem or a new um, yeah, any new result comes up when you ask questions like these. So I just want you to cultivate a habit of um, questioning whenever you come up with, I mean whenever you come across a new topic. So yeah, so you can think about it, and if you have any thoughts about these questions, then you can yeah, I think I'll just maybe give you my email, so that you can also use the forum, but if you explicitly want to reach out to me, you can reach out to me on this um, yeah, you can reach out to me on this email ID, and I mean regarding the course or any of the questions that we have discussed in the previous tutorials and so on. So yeah, so I think there is one question that we did not do today, but I would want to do it when there are more people around. You can think about this, and if you have your answers, you can share it in the next tutorial. So next we will meet on Friday, which is yeah, sorry, okay, I'm not sure what the date is, but yeah, next Friday 6 p.m. to 8 p.m. So in the usual slot. And yeah, I'll stop the recording.